Hi friends, as we get started on chapter 7 is all about roots and exponents, and we're going to be taking the things that we have learned from chapter 6 and chapter 5, and we're going to be expanding them into chapter 7. So again, we are just going to have more powers, more radicals, and the whole point again is to find an answer for x. So as we're getting more complicated equations and problems, these are more tools in our tool belt that we are going to get to use. So where does this fit in the big scheme of things? Well, in chapter 5, we were learning just about roots and radicals. And if you have your little handouts, we had the handout about radicals, review of radicals, what is a radical. We know that the number underneath is called our radicand. We know that our number here at the top is our index, and it tells us how many that we need. It's our instruction guide. And then we had our answer at the end. So we had our review of radicals that you could go over. We also had the simplifying radicals worksheet. That's a great one to pull out and make sure you have on hand so that you know how to simplify a radical. And there were some steps and some rules to combining those radicals. And so if we were once we were simplifying them and pulling out according to the instructions, in this case it was square root, then we could combine them if and only if they were playing on the same team. And then also we had our exponent rules from chapter 6. So this is a good one to have on hand as well. So some of the things that we had learned about roots and radicals in chapter 5 were that our index was our instruction guide to tell us how many of a number we needed to be able to pull out. And this number could be anything. We also looked at it where it was just a plain square root and it doesn't have the 2 on it. So the only difference between chapter 7 and chapter 5 is they call it nth root. So they're not all using this nth roots. N in math just means some other number. It's the first letter of the word number. And so now it's any number. So now instead of only working with square roots where we were looking for pairs of 2, like in this case it would be 4 times 4, it can be any number. So we might be finding cube roots, we might be finding 4th roots, we might be finding 9th roots. Any time that it's any number other than 2, it's just called an nth root. So not something new, just a different name so that we can describe it differently. They still work exactly the same. Our roots are still an instruction guide. It tells us what we have over what we need. And so we've got how many we have. We need to, do we have to? When those match up, we have that number 1, we can pull it out. Remember that we've often talked about it in the fraction form that way. There were the special things that when we had roots, if I wanted to add roots, both the root and the radicand underneath it had to be exactly the same. It couldn't be cubed of one and squared of the other. It also couldn't be maybe the square root of 2 plus the square root of 3. Those could not be added. So when we add them together, we had those rules. They had to be exactly the same. When we multiplied them together, the rule was that only your index has to be the same. And then we simply multiply the numbers underneath. So in this case, if we were multiplying the square root of 2 times the square root of 3, that would work. And we could have the square root of 2 times 3, which would now be the square root of 6. So there were those rules that we needed, and those rules are going to be important as we move forward. So then in chapter 6, we learned all about exponents. We learned that when we have exponents, we have the base number, which then ties back into these roots. Again, same thing. We have this base number. When our base is the same, then there were special rules where we could add this. And that is the this guide here, the exponent rules, you'll want to make sure to know how to work all of these really well. Have this printed out for yourself. Okay, we knew that when we have a power raised to a power, these are then multiplied together. If we have a power that's a negative, our rule for negatives all the time from the very beginning of math is that when I change sides, I get to change the sign on it. So, if we had x minus 4, if I change sides, this is now plus 4 because we've added it. So anytime we change sides, we change the sign. So it worked exactly the same for exponents. If I have a negative up here, my side that I'm going to change is in this fraction form. So now if I can put it on the bottom, it goes from being a negative if it's on top, and it would be a positive on the bottom. In the same case, if I had 1/6 to the -2, it's a negative on the bottom. I need to change sides. It'll change signs. Now I just have 6 squared up on the top. Okay. We learned that any exponent to the power of 0 is equal to 1 all the time. So those were some rules that we had. So we knew some rules about radicals. We know all of the rules about exponents. And so now we're going to move into having these two things work together. So what happens when you have something like I had shown initially, and we have a cube root of something times a square root of something else? Well, my radical rule says that these cannot be multiplied. They have different indices. Okay. But then I have these exponent rules that say if I have the same base, then they could be added. So is there a way that we can work back and forth between our different forms of our radicals and our exponents to use the rules that we have for each of them to help us solve for x? And this is just a part of learning all of the different tools and being able to work them together. And so since we know that math is consistent, God is consistent, He has created an order, that there is an order and there's nothing that has a gap or a flaw in it. And so in the same way that we have these roots and we have these exponents, yes, the answer is yes. There's a way that it can work together. We can have our root rules and we have our exponent rules. So first thing I want to do is go back and look at this square root of 16 that we have here. We know that this was an unwritten 2. And for 16 here, I might say that it's raised to the exponent of 1. So these are numbers that we can all agree on are the same. When I think of solving the square root of 16 here, when I talk about it in my have-need fraction form, say I have 1/16, I need 2/16. If I were to rewrite the square root of 16 as the square root of 4 squared, in this case, my base is 4, and I have 2 of them, and I need 2 of them, and so my answer ends up being 4. So if we take only our base here, so we're going to look just at our base, and I pull my base down, and I rewrite my numbers that I know for my radical as my fraction, I can rewrite the entire radical as a base with an exponential, with a fractional exponent here. So I would have 16 to the 1/2. I have 1, I needed 2. I could also take my 4 over here, this base, which is 4, and I could rewrite it as a fractional exponent. I have 2, I need 2, which really gives me the number 1, so 4 to the 1. So then we ask ourselves, are these two things the same? Because I've shown right here that they are equal to each other. So if they're equal, somehow we've got to be equal. So let's use some of our exponent rules that we know. we know that we've got that power to a power rule. So anytime I have a number with a power and I'm raising it to another power, I take these two things and I multiply them together. So if I can multiply, I can also divide, so I can back myself up. So I'm going to take my 16. I have 16 to the 1/2, and I'm going to take just this 16 and say, I know that 16 is equal to 4 squared. So I'm simply replacing my 16 with a 4 squared. And I'm leaving my 1/2. So now I have 4 squared to the 1/2 power. Now I have a power to a power. My power to the power rule says the one power, one exponent, is multiplied times the other exponent. So now I have my base stays, my 4 stays. My exponent 2 is multiplied times 1/2, which 2 times 1/2 gives me 2 over 2, which reduces to 1. So yes, I've shown that we can go from 16 to the 1/2, and it's equal to 4 to the 1/2 by using our exponent rules. So this is a way that now we get to be able to go back and forth between having something written as a root and having something written as an exponent, because sometimes our root rules will help us simplify. But sometimes it might be our exponent rules that help us simplify. So now we have a way to turn our number into the thing that makes it the easiest for our problem. So let's look at this one. If we're always thinking of it like this instruction guide, let's walk through what we had. In this case, I have 1, I need 2, so I would rewrite my base first. My base is 7. I have 1, I need 2, it would be written as 1/2. So this is something to get familiar with. Anytime you see 1/2, it means the square root of that number. Okay, so what if I had the cube root of 6 squared? My base is 6, so I'm going to simply write my base again as a 6. I have 2 of them. I need 3 of them, so this would be 6 to the 2/3. In this one, we have the 5th root of 3 cubed. 3 is my base. 3 is my base that I'm going to write down. I have 3 of them. I need 5 of them, so 3/5 is my fractional exponent. These forms are identical. Same exact answer. This is just, I wrote over here, the goal is getting comfortable moving back and forth. So we're just going from something that looks like a root to something that looks like a fraction. If I was working with roots and I had the square root of 7 times the square root of 6, then I know, according to my root rules, that I can multiply these. And this would be the square root of 7 times 6. But if I have the square root of 7 times the cube root of 6, I cannot multiply those. Sorry, let me redo this. Times the cube root of 7, I cannot multiply those. But in this case, if I rewrote them as fractional exponents, 7 to the 1/2 for this first one, times 7 to the 1/3, I have exponent rules that tell me when my base is the same, I can add my exponents. So as we can see, this is the knowing how to go back and forth means that sometimes we can use our radical rules to simplify. Sometimes we can't, but if we switch it to exponent rules, then we can. So that's the whole point of going back and forth with our nth roots for that. So on homework problems, you have 13, 14, 15, and 17 assigned. So I'm going to look at 13, and it says the 4th root of 14. So for this, it says simply rewrite the expression using a rational exponent notation. So when they say rational exponent, that's going to be a fractional exponent. So our base is the same. So we're going to write 14 down as our base. And then how many do we have? We have one of them. We need 4 of them. So the fourth root of 14 can also be written as 14 to the 1/4 in that case. So in the same way, we get to go backwards. So on homeworks, you've got 18 through 22 says rewrite the expression using radical notation. So in this case, on 18, they are giving us our fractional exponent there. So again, we're going to write our base, and then we write out our fraction, our radical here. And this is our have and our need. So our need is always going to be our index. So we're going to put our 3 where our index is, and we're going to put our 1 there. So this would be written as the cube root of 6. If you have ones like number 22, where it says 8 to the 7/4, again, 8 is going to be our base. We're going to put our radical sign. 4 is our index. That's how many we need. And we have 7 of them. In this case, for your homework, you don't need to simplify it. If we were simplifying it, I have 7 and I only needed 4. So I could rewrite this as 8 to the 4th times 8 to the 3rd. Because we know when our base is the same, our exponents get added. And then I have 4, I need 4. This 8 could escape, and I would have 8 to the 4th root of 8 cubed. So that's a way that would be fully simplified for your homework. It's not asking you to fully simplify them. Okay, so on your homework, as we're working through this, for the next section, 29 through 40, it's talking about evaluating an expression. And that just means use all of the rules that you know to be able to simplify or find an answer. So in the case, I'm going to do 29. That one's not assigned. 29 says the cube root of 64. If I was given the cube root of 64, again, there was 2 different ways we could write it out. I could write it as 4 times 4 times 4 and say, I need 3. I have 3, so these escape as the number, and my answer is 4. I could also rewrite it as 4 cubed. Now my index and my exponent match, so those cancel out, and I simply get my root underneath. So either way, I've got 4 as my answer there. Now, one of the things that's important to think about with our addition and subtraction with our roots, let's go back to taking a square root. When we were taking the square root of 25, and we had x squared equals 25. So back in our quadratics, I think chapter 5, where we were learning all about quadratics, and we had x squared equals 25. We learned that to solve this, we just take the square root of both sides. What you do to one side, you do to the other side. So if I take the square root of these, then when I take the square root of something that wasn't already squared, then I have to add that plus or minus in, because x can be both positive 5 and negative 5. And that was because we know in math that 2 negatives always equal a positive, and 2 positives always equal a positive. So as we are moving through roots, anytime, let's think about this, anytime we have an even root, so if we've got the square root, a 4th root, a 6th root, our index is telling us that we're having to make pairs. For the 4th root, I would need 4 of them, which is basically 2 pairs. Altogether, for a 6th root, I'm going to need 6 of them, which is going to be 3 pairs. So anytime we have an even index, the answers that we're going to get are always going to be two options, because they could all be positive or they could all be negative. If I had 4 negatives, I would still end up with a positive number. So if we're looking at our homework and we're seeing something that looks like the 4th root of 16, immediately I'm going to say I have an even number. Well, I know that 16 is 2 to the 4th, so I could rewrite that. So I could have positive 2 to the 4th, or I could also have negative 2 to the 4th, and they both give me 16. So when I have this 4th root and it's asking me to evaluate it, my answer is going to be plus or minus 2. Okay, so then let's think about odd numbers. When I have odd roots, 3, 5, 9, something like that. If I have a positive number underneath, say a positive 27 here, the only way that I can get a positive when I have when I have a set of 3 is to have 3 positive numbers. Because if I had 3 negative numbers, these 2 would be positive, and then positive times negative is negative. My answer would be negative. So for the cube root of 27, my only option is for it to be 3. If my answer was negative 3, then I would have the cube root of negative 27. Okay, and I know right now you're saying, okay, Miss Thomas, hold on. We have a negative under a radical. Isn't that I? Didn't we talk about I? We talked about I being the square root of negative 1, okay? Because it was an even root. And we cannot have an even root and have a negative number, because we just learned that. Because anytime we have an even root, no matter how many pairs we line up, if they're all negative, it's going to be positive. If they're all positive, it's going to be positive. Even if they're negative, it's going to end up being positive. So when we had this even root of the square root of a negative number, this ended up with something that we can't solve because it doesn't follow the rule. So we renamed it I as an imaginary number so that we could end up solving it. However, when we are looking at odd indexes here, we do have a way that we could get that negative number because it's odd. So yes, we are allowed to have negative base numbers if and only if we have an odd index. So if I have the cube root, if I ended up with I didn't mean to write that. If I have the 4th root of negative 27, we're going to have to deal with an I. And we're going to have to bring out that I and say the 4th root of positive 27, because even numbers have to have positive bases. But if I'm dealing with an odd number, I can have those negative bases. So if I had the 5th root of, say, 125, I could have it both positive, or I could also have the 5th root. If the 5th root of 125, if it's positive, the answer is going to be positive. If this was a negative, then the answer is going to be negative in that case, because I can have 5 negatives and they end up with the same negative thing. So that's how we work with our negative numbers and our roots. So let's look at number 30 in your homework. It says the cube root of negative 1,000. So the first thing that we ask ourselves, I have a negative number underneath my radical. Is that allowed? Well, I have an odd index. So yes, it is allowed because I can have three numbers that are all negative and they end up being negative. So what are those? Well, this has 3 zeros. I need 3 places. That makes it easy for 10. Because when you multiply tens, you just add the zeros in. So I could have negative 10 times negative 10 times negative 10, and that would give me negative 1,000. So my answer would simply be negative 10. I could also rewrite this as the cube root of negative 10 cubed. Now my index and my exponent match, so it all goes away, and I simply have my base for that. Let's look at 31. 31 says negative 6th root of 64. Now let's look at the difference between these two. In this first one, our negative was underneath the radical. It's inside. That means it has to be a part of all of your answers. Now on this one, our negative is on the outside, which technically means this is the number 1. So I could rewrite that as negative 1 times the 6th root of 64. So this negative is applied after I deal with my radical. In this case, my negative is applied while I work my radical. So let's look at 64. Just kind of break it down. I've got 2 times 2 times 2 times 2 times 2 because I know that 8 times 8 is 64. And each 8 is, there we go, a set of 3 2s. So I could write the 6th root of 8 squared. I could write the 6th root of 4 cubed. Or I could write the 6th root of 2 to the 6th. Let's see if these are all the same. Okay. If I switch this to our fractional exponents, I would write 8 to the 2/6, which gets simplified. 2/6 is the same as 1/3. So I've got 8 to the 1/3, so that tells me the cube root of 8. In this case, I'd have 4 to the 3/6. 3/6 gets simplified to 1/2, so I'd have square root of 4. In this case, I've got 2 to the 6/6. 6/6 gets simplified as 1, so I've got an answer of 2. So are all these all the same? Cube root of 8. Well, I know the cube root of 8 is 2. Square root of 4. Square root of 4 is 2. So all 3 ways, even though they looked different, one was a cube root, one was a square root, and one simplified out itself, they all gave me the answer of 2. So either way, any of the ways that you want to work that is fine. Okay, so now I have my 2. My 2 simply replaces my 6th root of 64, and I'm going to rewrite 2 right here. So now I have negative 1 times 2 gives me negative 2. So as you're going through your homework, when you have a negative on the outside, it's applied afterwards. When you have a negative on the inside, it's applied beforehand. Okay, let's work out, let's work out number 38. Number 38 says negative 25 to the negative 3/2. Okay, so before we get super complicated and we kind of freak out saying that's a whole lot of numbers, we're going to take it through the steps that we know initially. So first, this negative on the outside is the same as negative 1. So I'm not going to deal with it right now. When I look at 25 to the 3/2, I am going to make it positive. I don't like that being negative. So remember, if I change sides, I change signs. So I'm going to put this 25 down here. Now it's to the 3/2. Okay, so I'm dealt with a couple of different things that I want to look at. Now we can rewrite 25 to the 3/2 as the square root of 25 cubed, right? Because this is my have. I have 3. I need 2. Or I could go ahead and rewrite 25 as 5 squared. So now I have 5 squared to the 3 halves. Now using our power to a power rule, I have 2 times 3 halves. The 2's cancel out and I get 3. So I have simplified my 25 to the 3 halves to simply being my base, which is 5. 2 times 3 halves gives me 3. 5 cubed. So I'm going to replace. Now I have 1 over 5 cubed. Well, 5 cubed is 125. And my 1 times my negative 1 times here simply gives me a negative. So as we just baby step and take through what we have, in this case, we could have written it out as a radical and solved it and then said that I've got 5 times 5 times 5 times 5 times 5 times 5, and then go, I need sets of 2. Here's one set of 2. Here's another set of 2. Here's another set of 2. And I've got 1, 2, 3 5s that come out. And that would give us 125. Or we could rewrite it as fractional exponents and use our exponent rules to simplify quickly and get 5 cubed also. So hopefully you can see how sometimes using the radical helps us simplify faster, sometimes using the fractional. Same problem, different ways to work it out. Okay. Let me see. All right, so now, big picture. How do we use, I'm going to see if I have a, where do I want to go from here? How do we use everything that we have to actually solve an equation, okay? So again, as we were solving when we were dealing with quadratics, we have this equal sign now in the middle. Oops. We have the equal sign in the middle, and the whole goal is an answer for x, right? So now we have new tools in our toolbox to be able to find us some answers for x. So in this case, if I had x cubed equals negative 125, can I do that? Yes. We know that we've got x cubed over here. The opposite of an exponent is a root. But if it's 3, I have 3, then I would need to take the cube root of both sides. So I'm going to take the cube root of my left side and then the cube root of my right side. My cube root on my left side, my index and my exponent now match, so I simply have my base, which is x. Now my cube root of the right side gives me that negative 125 underneath the radical. Is that allowed? Yes. I have an odd index, so it allows me to have a negative radicand, okay? It's allowed. It also means that my answer has to be negative. That's the only way that I can get that. So I'm going to rewrite 125 as negative 5 cubed. Now my index and my exponent match, so my answer is negative 5. So did it double check? I had an odd index with a negative radicand, which meant my answer has to be negative, and I got a negative answer. So we have a check on that, and x would be equal to negative 5. Okay. So in this case, if I had x to the 4th equals 16, how do we solve for x? I would take the 4th root of both sides. Now on this case, I have an even index. So when I do an even index root, I'm going to have to do a plus or minus. Because anytime we have an even index, we are going to have 2 answers every single time, because we can have a positive answer that will get us there, and we can have a negative one that can get us there. So I've rewritten it out as 2 times 2 times 2 times 2. So I need 4, I have 4, my answer is 2. We could have written it as the 4th root as of 2 to the 4th, plus or minus 2 to the 4th. Those would match. So our answer is 2, so we'd have plus or minus 2. And we already talked about the i's here. So in this case, when we have a 1, remember the root of 1 is always 1. So in this case, I had the 9th root of a negative 1. Is that allowed? Okay. Odd index can give me a negative answer. Yes, it's allowed. So my answer would simply be negative 1 for that one. Okay. So how it works out in real life is we have this equation and they're wanting us to solve for s here. So as we're working through, we're going to go way back to the beginning and just do our regular rules. S wants to go to the movies by himself. How do we get him all alone? So in this case, we're going to divide both sides by 0.089, okay? And we're going to get S cubed, let's see, is 363, okay? So now that our answer becomes, I want S all by itself. I have it to the exponent of 3, so I'm going to take the cube root of both sides. So now I simply have S on one side, and then I have the cube root of 363 on that side. Now, the cube root of 363 doesn't work out all that well, so they say to just use the calculator on it. But I wanted to show that we can rewrite the cube root as 363 as 363 to the 1/3 power. We would use a calculator for that and get it to be approximately 7. Okay, so I'm going to pull up some of your homework for solving. So on 54, you have 6x cubed equals negative 1296. So the first thing is, remember, we were always looking for an answer for x. That's the goal. How do we get x by itself? So the first thing that we're going to do is we're going to divide both sides by 6. So we're going to have x cubed is equal to negative 216 here. And then I want x by itself. I have an exponent of 3, so I'm going to take the cube root of both sides. Can I have the cube root of a negative number? Yes, I can. My answer better be negative. So I have 3. I need 3. My answer is x. Now for 216, here is negative 6 times negative 6 times negative 6. So I have 3. I need 3. My answer is negative 6. We could have also rewritten it as negative 6 cubed. I have 3. I need 3. These match, so I simply have my base. I got my answer as a negative number. I knew my answer needed to be a single negative number, so I can say x is equal to negative 6. So that's the whole goal in solving. If we have a coefficient, we're going to divide by the coefficient, and then we're just going to take the root. And we're going to get to use our root rules and or our exponent rules to go back and forth between that. So a summary for 7.1 is to look at it and say, what's the index? So on this one, the index for our radical, remember, is always what we are looking for. So index here is going to be 7. The index, when we have it as a fractional exponent, is always the denominator, because this is I have over I need. So when we have our root form, our index is above our little radical sign. When we have it as an exponent, the index is always going to be your denominator. Okay? Know the difference between the negative of a radical and taking the root of a negative number. In this case, our negative simply sits out front. So we're going to work our radical first, and then we're going to have a negative answer. In this case, our negative sits on the inside. We have an even index and a negative radicand. So these cannot be worked without taking out an I. because I have that even one. Right? And you should be able to solve for x, use our rules. In this case, I have it x is cubed, so we are going to take the cube root of both sides. In this case, I have an entire base. Here, this binomial is squared. So I would take the square root of the entire binomial and the square root of the other side. So then now the base that comes out is x plus 4. And the square root of 0 is always 0. And we can solve for x in that case. In this one, we're going to get x by itself first. So we're going to move our 7 over, change sides. It changes signs. And I'm going to have x to the 4th is equal to 1,000. Then we take the fourth root of both sides. And I'm going to get x here. And then we've got the fourth root of 1,000. Okay? So which is 100 times 10. And so we'll just work through. And if it can't be simplified, then it just can't be simplified in it. Okay? So, 10,000. When I added that, should have been 10,000. And then I have 4 zeros, which makes it nice. So one of the things I do want you to notice is that when you have something like this, when we have the fourth root of 10,000, okay, this one's easy because it's a 10, but we could rewrite this as 100 squared. And so we can take our radical and our exponent because of the exponent rules and write this as 2/4 or 100 to the 1/2. So we could have rewritten this also as the square root of 100. So we can go down, we can make our index decrease if we can find a way to have an exponent inside that would simplify that fraction. And this can be beneficial when you're trying to add, because if I have another square root that I'm trying to add it to, I would want to turn it into a matching base so that I could add them together according to those rules. And that'll be something that we'll start working on later. But that's 7-1 wrap up.